Okay, well, I want to welcome everybody to the Spring 2014 Simons Lectures in Mathematics. And our speaker is Ian Agol. He received his PhD in 1998 under the direction of Mike Friedman. After a period on the faculty at UIC, he moved to Berkeley, where he's now professor of mathematics. Professor Agol has won a number of major awards, which I've mentioned just three: the Clay Research Award in 2009, the C.U. Berwick Prize in 2012, and the Veblen Prize last year. And this is the first of three lectures. It's on the virtual Haken conjecture. Let me just mention that because of the Schwartz talk later this afternoon, there won't be an official colloquium dinner tonight, but there will be after the lecture tomorrow. So I hope everybody will come to that. So Professor Agol.
Haken. Oh, Haken, yeah. That's Dennis is correcting. Yeah, thanks a lot for the invitation to speak. And I hope that these lectures are accessible, although I see a lot of the audience here are probably going to be boring. But anyways, that's the way it is. So, I want to talk about the virtual Haken conjecture. So in a paper by Thurston about 30 years ago in the Bolton AMS, he posed, well, he gave his sort of viewpoint on three-dimensional hyperbolic geometry and Kleinian groups. And at the end of the paper, he asked a set of questions, 24 questions, which have in some sense guided a lot of the research in the past 30 years in the field. And so what I want to talk about in these lectures is four of these questions having to do with so-called virtual properties of three manifolds. And I don't expect everyone to understand the phrasing of these yet. So actually the goal of this lecture will be to explain what these questions mean. So question 15, paraphrase, was, are Kleinian groups Lerf? And so I'll explain what those mean. So question 16, does every aspherical three manifold have a finite-sheeted cover, which is Haken? This was actually originated in a paper of Waldhausen in 1968, although it's maybe a little open to interpretation which question Waldhausen was precisely asking, but Thurston certainly asked it in his paper. And then question 17, does every aspherical three manifold have a finite-sheeted cover with positive first Bay number? And then does every hyperbolic three manifold have a finite-sheeted cover? Which fibers are the circle? This dubious-sounding question seems to have a definite chance for a positive answer. So Thurston wasn't conjecturing any of these, but he certainly asked them as questions. But somehow they get attributed to Thurston as conjectures. So the goal of this talk will then be able to explain what these questions mean. And I want to sort of put them in a little bit of historical context, and then the second lecture will explain then how they relate to a conjecture of Donny Wise in geometric group theory. So the second lecture will be on geometric group theory, and then explaining a certain overarching conjecture that Wise made. And so this lecture will be on three-manifold theory, then we'll talk about geometric group theory, and then the third lecture I'll discuss some aspects of ingredients that go into the proof of Wise's conjecture. So that's the plan for these lectures. So this talk, I'm going to talk about surfaces in three manifolds for a little bit, and then mention the Geometrization Theorem, and then talk especially about the hyperbolic case of hyperbolic three manifolds, and then talk a little bit about three manifold fundamental groups, and that will continue into the beginning of the next talk as well. So that's the plan for this lecture. So all the surfaces in the, will be assumed orientable, unless specifically they're not. But a closed essential surface is a surface. It's a map of a surface into a three manifold with either Euler characteristic less than or equal to 0, so like a torus or a higher genus surface, and which is pi1 injective, or it's genus 0, so two-sphere, and which is homotopically non-trivial. So that's all I mean by an essential surface. Although for the most part, we'll be discussing the case of Euler characteristic less than or equal to 0. And if we have an embedded pi1 injective surface in the manifold with Euler characteristic less than or equal to 0, then the surface is called incompressible. So this is sort of the classical terminology in three-manifold theory, having nothing to do with other notions of incompressibility.
One's embedded, right?
So yeah, these are maps of surfaces, and if it's an embedding, then it's called an incompressible surface. If it's embedded with all the characteristics less than or equal to 0, if it's embedded in a sphere and homotopically non-trivial, then it's a reducing sphere. So I'm, for the most part, going to ignore the definitions in the case of manifolds with boundary. There's just for some simplicity, although I'll give some examples of manifolds with boundary, but I'm not going to get into the definitions as much to avoid the case-by-case analysis. And if a manifold is M is aspherical, meaning that its homotopy groups vanish, higher homotopy groups vanish, and it contains a pi-1 injective surface, an embedded pi-1 injective surface, then it's called a Haken manifold. So an example, I'll give an example on the next slide, but if the first Betty number is positive, so the rank of the first homology is non-zero, then the manifold is Haken. So this follows from loop theorem, which I'll mention in just a second. So, oh yeah. Yeah, so aspherical manifold is equivalent to saying the universal cover is a contractible manifold. So in 3 dimensions, once pi2 and pi3 vanish, then the higher homotopy groups will vanish. That's a good question. Okay, so an example of the Haken manifold then is a fibered 3-manifold. So a fibered 3-manifold has a map to a circle such that the premajority point is a surface, codimension 1 submanifold, but a surface which is a fiber. So in 3 dimensions, this means that you have a mapping torus, so you have a homeomorphism of a surface to itself. So Fg will denote a surface of genus G. You take that surface and you cross it with an interval. And so you take the surface, cross an interval, and then you glue the top to the bottom. But there's many different ways you can do that. The product structure gives you identification of the top and the bottom. And so that map gives you, it's well-defined up to isotopy, so it gives you a well-defined element, actually up to conjugacy in the mapping class group of that surface. And mapping class group's a very large group, so you can get lots of different 3-manifolds this way. And so this is an example of a Haken manifold because the surface in this mapping torus will be pi-1 injective embedded, and therefore it's incompressible. So these are, if you want a good example of a Haken manifold, these are a wide class. So a motivating question then in 20th century 3-manifold topology is, if you're given an immersed essential surface in a 3-manifold, then does there exist an embedded essential surface of the same type? Of course, this is also a question, I guess, in higher dimensional topology, but in 3 dimensions, it's sort of of a different nature. And it's an important question in some sense because embedded surfaces tend to be easier to work with for 3-manifold topologists than immersed surfaces. For example, there's a theory of normal surfaces introduced by Conjecture and Haken that allows you to answer certain algorithmic questions having to do with embedded surfaces that are, for example, like the unknot recognition algorithm of Haken has to do with embedded disks. And working with embedded surfaces tends to be easier than working with the immersed surfaces. So that's maybe a motivation for, for this question. So examples include Dane's lemma, which Dane claimed in 1911, although there was a mistake found in his proof, and Papakyriakopoulos actually found a proof in 1957. So if you have a manifold with boundary, you have an embedded loop in the boundary, which is homotopically trivial in the manifold, then it actually bounds an embedded disk. So for example, if you have a knot whose fundamental group of the complement is Z, then it's actually the unknot. That follows from Dane's lemma. And the loop theorem also proved in the same paper by Papakyriakopoulos, which is a similar statement for an immersed loop. But if there's so in Dane's lemma, that loop bounds a disk. If there's an immersed loop that bounds a disk homotopically, then there's some other embedded loop that bounds a disk that's essential. I haven't phrased it precisely, but
Okay.
The Sphere Theorem, proved also by Papakyriakopoulos, says that if The second fundamental group is non-trivial. In other words, there's an immersed essential sphere. That's not completely obvious that pi 2 is non-trivial. There's an immersed sphere. And I'm not going to get into the details of what immersed means, but anyways, if pi 2 is non-zero, then there's actually an embedded essential sphere in the manifold. Embedded meaning it's embedded, essential meaning that it's non-trivial on pi 2 and embedded. So, and it's not necessarily, the embedded sphere is not necessarily homotopic to the, say, some immersed sphere you started with. You might have to replace it with a different sphere. And then the annual-Centaurus theorems, which try to extend this, proved by Jacob-Schalen and Johansson in a Haken manifold, so a manifold containing an incompressible surface already. If there's an immersed essential annual-Centaurus, so those are the surfaces of Euler characteristic 0, then there's an embedded one. And then this was generalized in a certain sense to the Cipher fibered space theorem. So if you have a manifold who's a three-manifold with non-trivial center of the fundamental group, and in 3 dimensions that turns out to be a very restrictive condition, then and the manifold is aspherical, then it's Cipher fibered. So I haven't defined what Cipher fibered means, but roughly it's built out of a circle bundle over a surface. So it's sort of built out of a 2-dimensional manifold by a kind of foliation construction. And it was known to Waldhausen, though, that there's an infinite class of aspherical Cipher fibered spaces which are non-Haken. And these are sort of the hard case of this theorem proved by a bunch of people in the 90s. Now, a discovery then of Thurston. So a lot of this work was previous to Thurston's work, and then Thurston discovered in the 70s that, in some sense, most knot complements emit a geometry which is modeled on hyperbolic geometry, which I'll discuss in just a second what that is. And there's a trichotomy for knots. You either have torus knots, which are on the surface of a donut and are a curve lying on that, or a satellite knot, which can come like a connect sum of 2 non-trivial knots, or you take a non-trivial knot and you take another knot that sort of orbits around it, which is why it's called a satellite knot. And if you do that in some essential way, then you get so-called satellite knot. So connect sum is a special case to that, because you can view either knot as orbiting around the other one. You could shrink this knot down and then think of it as being a satellite of that one, or vice versa. And then there's the ones that aren't of these classes are the hyperbolic knots. So Thurston proved this sort of trichotomy. And this was a manifestation then of his geometrization conjecture. Oh, yeah, I'll say that in just a sec.
Okay.
So its complement has a complete hyperbolic metric. So the classic theorems I had about immersed versus embedded surfaces now are in some sense superseded by the geometrization theorem, which was question 1 from Thurston's 1982 list of questions. And this states that an irreducible 3-manifold, so here, if I assume irreducible, then you should think like an aspherical manifold by the Sphere Theorem, or maybe a 3-manifold with finite fundamental group. Then it emits a possibly non-orientable incompressible surface of Euler characteristic 0, so basically a collection of tori and Klein bottles, which is unique up to isotopy, unique up to some sort of wiggling condition. And each component of the complement emits a complete, locally homogeneous Riemannian metric of finite volume. And there's 8 possible geometries that can occur for these manifolds. So this question was proved by Thurston for Haken 3-manifolds, in particular for knot complements. So what I stated in the previous slide is a special case of this geometrization picture, and he conjectured it to hold in general, and then the proof of it was given by Perelman 2003 using Ricci flow technique of Hamilton, and pretty much not using any of the techniques that Thurston had introduced. It was a pretty independent proof. And for this, Perelman did not receive the Fields Medal or the Clay Millennium Prize. But of these 8 geometries, only 6 can occur for a spherical 3-manifold. So I'll talk a little bit about the geometries now. Only 2 are needed when the manifold itself is not geometric. So in other words, when there's a non-trivial, when the surface indicated here is non-empty, then the geometric pieces will only come in 2 flavors. And these are hyperbolic and hyperbolic cross R, so a sort of product structure that occurs in the Cipher fiber case. So if there's no geometric piece which is hyperbolic, then the manifold is called a graph manifold. And these include the torus and satellite, well, the cables of torus knots that, in the case of knot complements, the graph manifolds are a very special type. They also occur in links of plane curve singularities, for example. And this class has been sort of much better understood in the literature than the manifolds that contain a piece with geometry modeled in hyperbolic space, in particular on the hyperbolic manifold. So the most interesting, well, to me maybe, is geometry is the hyperbolic one. So one possible model for this, if you took a chunk of glass sitting on a table, and this glass has the property that the speed of light is proportional to the height above the table. So it'll take infinitely long for it to reach the table because it slows down proportional to its distance. Then light will follow a geodesic path in the glass, which is either a semicircle perpendicular tabletop or just a vertical line perpendicular tabletop. And in theory, if you took a chunk of this glass and mirrored the sides of it, then you would see this kind of 3-dimensional kaleidoscope that would be a model for a 3-dimensional hyperbolic manifold. In the second talk, there'll be a picture of what that could look like. So hyperbolic manifolds then are sort of modeled on this geometry. So I'm not going to get into the definition of Riemannian geometry, and well, I could say homogeneous geometry means the universal cover has a metric in which any 2 points, there's an isometry sending one point to another point. And so hyperbolic geometry is actually not only homogeneous, but it's isotropic. So any direction that you look, the metric looks, there's an isometry that fixes a point and sends any vector to any other vector. So it has a Riemannian metric of constant curvature -1. And the fundamental groups of such manifolds, it's a complete metric, just complete in the sense of metric geometry. And the fundamental group of such a manifold is called a Kleinian group. So if it's finitely generated. And actually, the case of manifolds with infinitely generated fundamental group is sort of completely not understood as far as I know. There's not even a conjectural classification of them. So classic examples of hyperbolic free manifolds then are there's the Cipher-Weber dodecahedral space, which is you take a dodecahedron and you glue opposite sides together in pairs in the way indicated in this diagram. So you glue it with a little rotation. And it turns out that this has a hyperbolic metric. It's a closed manifold. And you can make it out of a hyperbolic polyhedron where all the dihedral angles are 2 pi over 5. And it turns out that the faces are glued together 5 around an edge. And so everything works out nicely from the Poincare polyhedron theorem to give you a metric on the closed manifold. Now, these other 2 examples, the figure 8 knot and the Whitehead link complement, they admit a hyperbolic metric, a complete metric of constant negative curvature of finite volume. And it's a particular model for what the geometry looks like at the knot. Sort of the knot's been, in some sense, pulled out to infinity like taffy, and the geometry gets thinner and thinner and thinner as you go out the end of the manifold, which has this complete metric of infinite diameter. And there's a pretty good picture of what the geometry looks like out those so-called cusps. Okay, so these are some examples then of hyperbolic manifolds, and in particular Kleinian groups. Well, okay, so that's not a very precisely formulated statement. So so most knots being hyperbolic, what do you mean by most? There's many different measures on the space of knots. So it turns out that if you look at like alternating knots, for example, then you just enumerate them for some number of crossings, and most of those will be hyperbolic. So that's maybe one way in which they are. But yeah, I don't actually have a good, precise way of formulating that. So you get many other closed hyperbolic manifolds by an operation of Dayton filling. So you can take a knot and you remove it out of the 3-sphere. So we think of this knot as sitting inside of R3 compactified in infinity to get the 3-sphere. And we glue in a solid torus so that the meridian of the solid torus, the loop going around, if you cut it, you would chop the solid torus into a ball. We attach that to this solid torus, but using a non-trivial homeomorphism of the torus, which this curve is sent to a curve that wraps p times around the meridian and q times around the longitudinal way. So I can't quite draw the whole curve. It would be a little complicated. But for any rational number like this, there's a unique way to glue this torus to here and get a closed manifold. So what Thurston proved is that for all but finally many Dayton fillings, all but finally many rational numbers, the Dayton filling on this figure 8 knot complement is a hyperbolic free manifold. And this works for any hyperbolic knot complement or cussed hyperbolic manifold more generally. So this gives a way of producing lots and lots of closed manifolds that have a hyperbolic metric on them. Now, Thurston also proved that these Dayton fillings, the hyperbolic ones, are not Haken manifolds. They don't contain any closed incompressible surface. So this shows you that, again, there's lots and lots of examples of manifolds that don't contain these closed incompressible surfaces. And this was sort of frustrating to 3-manifold topologists because Thurston's original geometrization theorem only applied to manifolds that contain a closed incompressible surface. And it sort of led to the question as to how prevalent are these Haken manifolds, and in particular, if you're given a manifold, can you find a finite-sheeted cover that has an embedded pi1 injective surface? So that's the sort of question that we're considering in this talk. So that's a virtually Haken manifold. So if we have a compact aspherical 3 manifolds, the universal cover is contractible, then it's Haken if it contains an embedded pi1 injective surface. The Cipher Weber space, it turns out, is a non-Haken manifold. That was proved by Burton, Rubinstein, and Tillman. The original proof used many CPUs at computer time. Now you can actually download their software and check it for yourself on your own computer. But it's not a proof that's written down in the literature. It's a computer-aided proof. And as I explained already, the hyperbolic surgeries on the figure 8 knot complement are non-Haken manifolds. The 3 manifold is called virtually Haken if there's a finite-sheeted manifold cover such that that cover is Haken. So an example of a theorem of this sort, so Dunfield and Thurston proved in around 2001 that all of the Dayton surgeries on the figure 8 knot complement are virtually Haken. And actually there's a vast literature on the subject, which I'm not going to mention all the names in this talk, but there was a whole lot of special classes of examples of 3 manifolds that were shown to be virtually Haken over the past couple decades. So as I said before, Waldhausen conjectured that every aspherical 3 manifold is virtually Haken. That's question 16 in Thurston's list, and I think now we have the definition completely down. So, and a stronger question than of Thurston was whether there's a finite-sheeted cover that has first Bailey number that's positive. So a manifold is virtually fibered if there's a finite-sheeted cover that fibers over the circle. So if it fibers, then its first Bailey number is positive. So this is a stronger question than the previous question. And there's also a lot of work done on showing various classes of hyperbolic 3 manifolds virtually fiber, including the two-bridge links shown by Walsh, some monosinus links, and certain alternating links. So there's a literature on this subject again over the past couple decades. And so this is question 18 in Thurston's list, and he restricted this question to hyperbolic three manifolds, though not aspherical three manifolds. Because it turns out that, well, as I'll mention, that there's certain manifolds that are not virtually fibered. So to understand these questions, then, I want to say a little bit more about essential surfaces in the hyperbolic three manifold. So this, there's a picture that came out of Thurston's proof of the geometrization conjecture for Haken manifolds. And there's a dichotomy for surfaces, essential surfaces in hyperbolic three manifolds that was discovered by Thurston and proven by Waldhausen in general. So they're either geometrically finite or geometrically infinite. The first case includes quasi-Fuchsian surfaces. In fact, if it's a closed hyperbolic manifold, then a geometrically finite surface is precisely a quasi-Fuchsian surface, which I'll have a picture of in the next slide. In the geometrically infinite case, the surface is, so what came out of Thurston and Waldhausen's work is that the surface is virtually the fiber of a fibering of a finite-sheeted cover of the manifold. So in the case when the manifold fibers are the circle, the fiber surface is not quasi-Fuchsian, it's not geometrically finite in any sense. And so more generally, there's this similar dichotomy for finely generated subgroups of a Kleinian group that was proved by myself and Caligar and Gabai, the tameness theorem, a conjecture of Marden and refined by Thurston. And the covering theorem of Canary implies that if you have a subgroup of a Kleinian group, it's either geometrically finite or it corresponds to a virtual fiber of a fibration. So I think this gives some underlying motivation for Thurston's questions. Thurston was originally very surprised at the existence of
A subgroup.
a finely generated subgroup.
Any subgroup.
A finely generated subgroup of a Kleinian group is either geometrically finite or it corresponds to a virtual fiber.
It's a surface group.
It's a surface group. Yeah, exactly.
Finely generated subgroup is a surface group. Yeah.
In the second case, if it's geometrically infinite, yeah. You can have lots of geometrically finite free subgroups, for example. They have limit set, some Cantor set.
What is a geometrically finite group?
Oh yeah, so I didn't state it. So here's a picture of a quasi-Fuchsian surface group. It's a group that, so there's this circle, quasi-circle. Topologically, it's a circle, but it has Hausdorff dimension greater than 1. And this is on the complex plane. So this is the sphere. This is the tabletop in hyperbolic geometry, or the sphere at infinity of hyperbolic space. And there's a certain Mobius group that preserves this circle. And it turns out that there's a fundamental domain for this action on which the group acts co-compactly, and it's a convex fundamental domain. So that's a geometrically finite group in general has this property that there's a convex fundamental domain for the action of the group, which the quotient is finite volume. That's the way geometrically finite. And it turns out in the fibered case that doesn't happen. What's it?
It's a fundamental domain. Large.
Okay, so there's
Surface.
Just say it again. Just say it again. Yeah. What's the geometric?
Oh yeah. Sorry. There's a yeah. I shouldn't have said fundamental. There's a convex subspace, a hyperbolic space.
Space. Yeah.
Yeah, that's preserved by the group action such that the quotient has finite volume. It's a three-dimensional convex subset. So in the case of in the two-dimensional case, this would correspond to a surface of finite Euler characteristic, it turns out. But in 3 dimensions, there's this there's these geometrically infinite model that Thurston discovered.
You mean in the two-dimensional case?
Yeah, it's sort of Fuchsian group.
Riemann surface.
Yeah, Riemann surface.
It's finite. It's finite area.
It has finite. Yeah, so there's a convex core that has area equal to, by the Gauss-Bonnet theorem, minus 2 pi times the Euler characteristic, and that's sort of what corresponds to the geometrically finite 3-dimensional case.
Does it have a bounded subharmonic function?
So bounded. Yeah, that's right. So you can put like a value 1 here and value 0 here and extend that to harmonic function. That'll be invariant in the group action. That's right. And actually, yeah. So there's harmonic functions that go into the proof of Alfor's measure conjecture using this tameness conjecture. The case of the geometrically infinite surface group So the figure 8 knot complement, it turns out to the fiber over the circle. The fiber is a genus 1 surface, but its limits, so it has limits at the entire sphere at infinity. It's a normal, when you have this fibration of the circle, the surface group is a normal subgroup. So its limit set is the same as the limit set of the entire group. And so you can't really draw a picture of this circle, but it's actually a sphere-filling curve. So Cannon and Thurston realized there's this sort of piano curve picture going on. And you can see it sort of from this picture approximately. So if you want to describe a sphere-filling curve, it's usually done by a sort of limit of approximate curves. And here, there's one piece of the curve that's this disk. There's another complementary piece on the outside. This disk is actually made of certain limit sets of Kleinian semigroups that whose limit set is an arc, and it's piecewise made of these arcs. And you can sort of piece these together to get the the limit set. And this gets subdivided into two fractal regions, and then each of those guys get subdivided. And so what the sphere-filling curve does is it fills out this region, and then it fills out the complementary region. But it fills out this region first, this region, and this region. And it fills in this region by first doing this one and then this one, and then marches over here. And so you can iteratively describe these this piano curve by seeing how it traverses these various regions. So it's kind of a similar picture if you're familiar with the examples of piano curves or Hilbert curves, where you can describe as a limit of curves that march through certain regions in an order. So that's to give you some idea of what a geometrically infinite surface group looks like. Okay, so analogous to the loop, sphere, and annulus and torus theorems, these classical three-manifold topology theorems, you can ask, given an essential map of a surface into a manifold with Euler characteristic less than 0, is there an essential bedding of the surface into the manifold? And, well, the general answer to this question is no, because we know that there's lots of non-Haken three-manifolds. They can't contain any embedded incompressible surface, and yet there was examples of Cooper and Long that showed that, for example, these figure 8 knot complement Dane fillings, they're non-Haken, but they contain lots and lots of immersed essential surfaces. So that was proved in 2001 or so. And as I mentioned before, Dunfield Thurston showed that those have finite-sheeted covers that have positive first Bay numbers. So you have these immersed surfaces, but there's no way you're going to find an embedded essential surface. And note that the reason positive Bay number is sort of non-trivial, closed three-manifolds have fundamental group that has a balanced presentation, the same number of generators as relators. So if you look at a generic three-manifold, say by gluing two handlebars together generically, then most likely it's going to have first Bay number equal to 0. So this shows why having positive Bay number is sort of a non-trivial condition on a three-manifold. You just don't expect it generically. So given an essential map of a surface into a manifold with Euler characteristic less than 0, then there's no hope to get an essential bedding. But with further hypotheses on the surface, sometimes you can get a weak answer to this qualified yes to this question. So Gabay proved that if you have a surface which is homologically non-trivial, so it's representing its image on H2 in the manifold is non-zero, then he proved there's an embedded essential surface, incompressible surface that's embedded, and such that the Euler characteristic of this embedded surface is at least greater or equal to the Euler characteristic of the immersed surface. So if you like, if you take a Gromov norm minimizing surface, then there's an embedded Thurston norm minimizing surface. So this was, Gabay proved that Gromov norm equals Thurston norm, if you're familiar with those concepts. But anyways, this shows that under certain hypotheses with negative Euler characteristics, you can get to be embedded. But having non-zero H2 already implies that your first Bay number is positive. So again, this is not going to apply to many three-manifolds. So Gabay's proof makes use of sort of an inductive method called sutured manifold hierarchies to construct a foliation of the manifold with an embedded compact leaf, and then obtain the lower bound on the Euler characteristic via considering the Euler class of this foliation. So it's a nice argument. Well, in 2009, Kahn and Markovich, Kahn used to be here, they proved that hyperbolic three-manifolds contain immersed quasi-Fuchsian surfaces. And these quasi-Fuchsian surfaces are arbitrarily close to being totally geodesic. So if you look at the limit set of these surfaces, it's a circle in the sphere at infinity hyperbolic space, in the complex plane, if you like. And you can make it as close to being a circle as you like in Hausdorff distance. The Hausdorff dimension is always going to be, unless it's a round circle, it's always going to be greater than 1. But you can make it as close as you like to being a round circle. And these things will sort of exist anywhere. So any tangent plane in the manifold, you can find one of these surfaces that lies very close to that, and with curvature very close to -1. Oh, right. Markovich was here as well. I forgot. Yeah.
Last 2 weeks.
Cool. All right. So, and there was a nice conference that Dennis hosted here, I think, and where I learned about their work in more detail, which is great. Yeah, so previous work on this problem, again, as I mentioned the work of Cooper, Long, and Lee before, they proved that many Dane fillings on cusp hyperbolic three manifolds have essential surfaces, and then it was extended by Masters and Zhang to multi-cusps, like the Whitehead link. And then in 2008, Lackenby, right before their work.
Fast for me, and I don't know this topic.
Yeah, okay, so.
Fast for other people, too.
Yeah, no, sorry, there's a lot of definitions and.
Okay, wait, so where are you now?
Okay, so I was trying to give some of the history of this problem.
All right.
So yeah, let me just go back a step. So Thurston asked these questions about whether manifolds are virtually Haken. And if you had a finite-sheeted cover that's Haken, then it contains an embedded incompressible surface. Well, you push that downstairs, and you get this surface that's immersed. So it was also a natural question. It's stated like in Kirby's problem list. Does every hyperbolic manifold contain an immersed pi1 injective surface? And that's what Kahn and Markovich answered. And so what I'm just giving here is there was some previous work that had proved this from certain classes of hyperbolic three manifolds done by these people. So Lackenby, for example, proved it for arithmetic three manifolds in 2008. And I don't have time.
Group?
Yeah, the fundamental group's an arithmetic group. Yeah, sorry, I don't have time to go into the definition of arithmetic, but it's a fairly large class of manifolds. So, so this was an interesting problem with respect to Thurston's questions because it was certainly a necessary condition if Thurston's questions the answer was yes. What wasn't quite so obvious then was you have these immersed surfaces. How do you find a finite sheeted cover where they embed? And so in 2011, then, Wise, actually he had an announcement that appeared in 2010, but his result wasn't disseminated to 2011. So he showed that Haken hyperbolic three manifolds are virtually fibered. So if you already have an incompressible surface, then he showed that there's a further finite sheeted cover you could take that had this nice fibration structure over a circle. And so this statement was actually a special case of a much more general theorem of Wise, which the general statement requires geometric group theory, and I'll state it in the next lecture. So Wise's preprint is around 185 pages or so, and also depends on previous work of his with his collaborators Hagelin and Shu. But this theorem includes non-compact hyperbolic three manifolds. Well, I gave 2 examples at the beginning of the figure 8 knot and the Whitehead link, and those are already known to be fibered, but it applies to many more manifolds than that, which are not previously known to be virtually fibered. So what I proved in 2012 then is key relations with hyperbolic fundamental group are virtually special. So I don't expect anyone here to understand what that says, but that's what the goal of the next lecture will be, to explain this. But the corollary of this theorem then is that if you have a closed hyperbolic three manifold, then its fundamental group is LERF, which I'll explain in the next slide. Large means that there's a finite sheeted cover that surjects onto a free group, so it's much stronger than having positive Bay number, and it virtually fibers. So these resolve Thurston's questions 15 through 18. And the proof of the theorem actually makes key use of Wise's results, in particular a technical result of his, which I'll try to explain in the third lecture, the Mal-normal special quotient theorem. Okay, so what is this LRF condition? This stands for locally extended residual fineness. This is a classical. Oh, yeah, I'll have to explain that in the next lecture. It's, yeah, so, yeah, briefly, the Kahn-Markovich surfaces are used via theorem of Sagiv to cubulate a manifold. So you get an action of the three-manifold group on a cat-0 cube complex. And then it has hyperbolic fundamental group because it's a hyperbolic manifold. And then this theorem applies and says that it has a finite-sheeted cover that embeds in a right-angled Artin group, which has all these nice properties. So it's inherited. The idea is you find a finite-sheeted cover that embeds into this nice group, namely essentially a reflection group, and then it inherits all the nice properties of that larger group that it sits inside.
So
that's
relation.
Yeah. So I'll explain all this.
That theory.
That's right.
Okay.
So yeah, I apologize that there's so many definitions, but I didn't want to sort of.
What's the short?
Yeah. So I'm not going to explain the precise definition of LRF, but what it allows you to do is, suppose you have this hyperbolic three-manifold in a covering space whose fundamental group is a surface group. Now, there's general theory of Friedman, Haas, and Scott that allows you to promote that surface to an embedding, even if you just know the fundamental group is there. But what Scott's criterion says is if I have any compact subset of this covering space, then, and if it maps down here with a lot of double points, I can find a finite sheeted cover where this compact set lifts to or projects to an embedding in the finite sheeted cover of the manifold. So you have a compact subset that maps down with lots of singularities, self-intersections. Then you can find a finite sheeted covering space where it embeds nicely. And so this is sort of interpreting these classic questions in the case of Euler characteristic less than 0. So you can ask whether if I have a surface and it's immersed in the manifold, like one of these Kahn-Markovich surfaces, then can I find a finite sheeted covering space where it embeds? And this is precisely related then to the virtual Haken question. So this shows that question 15 in Thurston's list, together with Kahn-Markovich's theorem, implies question 16 and, in fact, 17 as well and 18. So I'll explain in the next lecture how those are related. And then, so this gives an extension of the classic questions about immersed versus embedded. So now, instead of asking for an immersed surface to be embedded, we can ask, does it embed in a finite sheeted covering space? Now, it turns out that not all three-manifold groups are LRF. There's examples of Niblo and Wise that show that the fundamental group of the complement of this link is there's certain subgroups there that are not separable. And in fact, there's examples of Rubinstein and Matsumoto who showed that there's certain graph manifolds, these non-geometric manifolds that are made out of H2 cross R geometries, which contain surfaces which don't lift to an embedding in any finite sheeted covering space. So in general, this question, the answer to this question is no, that you can't, if you have an immersed surface, you can't lift it to embedding in a finite sheeted covering space. But it turns out that in the hyperbolic case, that you can. Also, Thurston's virtual fibering question was stated for hyperbolic three manifolds, and it's for that class because it doesn't hold for general three manifolds. But again, recently, in 2012, Shizitsky and Wise showed that if you have an aspherical three manifold, which is not a graph manifold, then it has a finite sheeted cover that fibers over the circle.
So there's one hyperbolic piece.
At least one hyperbolic piece. The simplicial volume is greater than 0. Then it'll be virtually fibered. So, in fact, the graph manifold case, the ones that are virtually fibered were completely characterized by Svetlov, but it's a little involved to state it. But if you take, for example, the unit tangent bundle to a closed surface of a negative Euler characteristic, then that's not virtually fibered. So, whereas the sort of Milnor fibers that occur in a plane surface singularity, those are obviously fibered. I mean, they're fibered from the Milnor fibration. Those are examples. So there are graph manifolds that do fiber or virtually fiber, but there's also ones that don't. But that's been essentially completely worked out in the 90s. Okay, so the next lecture will focus on introducing the concept in geometric group theory, explaining why is this conjecture. I'll define hyperbolic groups and cat-0 cube complexes, and then I'll be able to describe the results of Wise And then the third lecture will be to explain how to deduce the virtual Haken conjecture from Wise's group theoretic conjectures. And I'll discuss some aspects of the proof of Wise's conjecture, so answering Thurston's questions. Okay, so I think that's it for. Oh, that's yeah, John.
Conjecture is a theorem?
Yeah, exactly. It's a theorem that I stated a few pages back that's a theorem I'll focus on.
I was just wondering if I knew that Stalling formulated the Poincare conjecture in terms of a group theory question, and you're suggesting that many of these new questions are also reformulated in terms of can all these theorems about group, all these theorems about three manifolds be reformulated in terms of group theory?
That's a good question. So can all these questions be formulated in terms of group theory? Well, certainly the virtual fibering can, because the notion of fibration is just that you have a homomorphism to Z whose kernel is finitely generated. And is that what you're asking for?
Put in do they correspond to theorems in group theory that then you specialize to get the theorems about three manifolds?
Yeah, well, unfortunately, so the Stallings has this formulation of the Poincare conjecture, and the only proof we know of the Poincare conjecture so far is via Ricci flow and all that. So, but yeah, I'm not sure exactly what you're getting at.
Since it's true, that statement in group theory is true, and it corresponds to the Poincare conjecture. So I just wonder if you knew statements in group theory that, by whatever hook or crook, are equivalent to these theorems about group theory. I just wondered if they're embedded in group theory.
Well, the geometrization conjecture certainly has a formulation that's purely group theoretic. Although
you'd have to assume the group was a fundamental group of a three manifold.
Right. So you could say it's a PD3 group. That's still an unresolved conjecture. So it's conjectured that. Yeah, that's right.
Okay.
But yeah, I guess to say that something is a three manifold group, it's hard to say that without saying it's a three manifold group theoretically. But PD3 is one way to say that, but that's still open.
You don't know what PD3 is.
Right, yeah. Anyways, these are a memory of Bill Thurston's. So next lecture, I'll talk about geometric group theory. That's it for today.
You did it all in 15 minutes.
I finished early? Okay. Well, yeah, okay. Should I start with the next lecture? I could cue it on up. At Berkeley, the next one will probably be a full hour, but Berkeley, all our seminars are 50 minutes, so I guess that's what I'd planned for.
Okay.
Are there any questions? There's just lots of fun questions.
Yeah, questions?
PD3 group?
PD3, yeah, Poincare duality, three-dimensional Poincare duality group. So this means that there's a fundamental three-dimensional homology class such that when you cap it with any cohomology class, you get an isomorphism. So it's with any coefficients over any ring and or any module structure of the fundamental group. So an n-dimensional closed aspherical manifold, the fundamental group is a PDN group, and it's known that PD2 groups are actually surface groups. I think you probably need to assume finite generation and finite presentation PD3 groups are conjectured to be three manifold groups, but that's still wide open.
The whole homotopy type to express the fact that cohomology satisfies Poincare duality. And you call that PD3 group. And
right.
All such groups are fundamental groups of three manifolds. That's the conjecture.
Right, and I think it's false in higher dimensions, but I'm not sure what the status of that is. So one possible approach to this is to try to get some coarse formulation of the geometrization conjecture, and aspects of that are in place. The Cipher fibered space conjecture I alluded to, I think can be done in the category of PD3 groups, I believe. So if you have a PD3 group with non-trivial center of the fundamental group, I think that implies it's a Cipher fibered space from the Cipher fibered space conjecture. But I'm not completely certain about that. But anyways, it's an interesting question whether these PD3 groups are actually three manifold groups.
So is there any hope that we start three manifolds which do not have a Z2 in this finite group? Then try to prove this kind of thing without using geometrization conjecture. Then to prove geometrization, because if that is fiber by sub, geometrization is known. Another way.
Yeah, so if there's a Z-squared subgroup.
Yeah, and you have to try to prove geometry, some part of geometrization conjecture. Without each flow, then you can try to prove that that's something you start from this. Then you can just prove this, what you explained, without using geometrization.
Well, so that's the point of the Cipher fiber space conjecture that I mentioned due to Gabai and Casson-Young-Rice and Mess and others, so that if you had, it was known pre-Perelman, or that if you have a three-manifold, it's a aspherical three-manifold that has a Z-squared subgroup of its fundamental group, then it actually satisfies the geometrization conjecture. So that was proved. That was proved before Perelman's work. I mean, it also follows from geometrization, but it was proved in the 90s. So
if it contains Z2.
if it contains Z squared, yeah.
So my question doesn't contain this.
Oh, it doesn't contain Z squared. Oh, sorry. Yeah, no, that was what people were working on. The idea was that to try to show that hyperbolic groups, which I'll mention in the next talk, are defined by, they have a linear isoparametric inequality. So if you had, the idea was that you would try to show that either a group has a linear isoparametric inequality or it has a quadratic isoparametric inequality, and then try to show that implies there's a Z-squared subgroup. So that would imply that if you had no Z-squared subgroup, then you were hyperbolic. And there was people who were trying to do that, but no one's figured out the approach to that. But that would be a possible approach to the PD3 question.
So if you just assume fundamental group is hyperbolic, without assuming manifold is hyperbolic, we can prove these kind of things?
No, that's still open. That's called the Canon conjecture, yeah. But there's a good approach to that now. If you can carry out the Kahn-Markovich approach in the context of these hyperbolic groups whose boundary at infinity is a sphere, then that would imply that they're actually Kleinian groups. So that follows from my work and an application of my work by Markovich. But so far, Kahn and Markovich haven't been able to do their surface construction in these hyperbolic groups, the PD3 hyperbolic groups. So that's still open.
But even if you could do all of this, you're not going to fix the finite fundamental group case.
Yeah,
That's different.
yeah, the finite fundamental group case, there's these finite groups that are periodic or something, and then they were mostly classified. I don't know, Jack probably knows a lot more about that.
They're certainly classified. Groups are classified, yes.
But I think there's a few exceptional cases that couldn't act on S3, but were not quite ruled out for various reasons. And there may be some claims by Ronnie Lee or other people that they could rule them out, but I don't think that was ever worked out.
But again, even if the group is right, is the manifold right?
Yeah, that's true, yeah. Well, when you're talking about groups, then I guess...
Thank you very much.
All right, thanks.
I have one more question. Oh, yeah. LERF.
Yeah, locally extended residual finiteness.
What?
Locally extended residually finite. Yeah, I had it at the top of the slide. Sorry. Yeah, so residual finiteness I'll explain at the beginning of the next talk. So that means that you know what residual finiteness is? So this means, yeah, so you have a subgroup, and for any element that's not in that subgroup, there's a homomorphism to a finite group that sort of corresponds to this finite cover where that element is not contained in there. So you look at the elements that send this surface to intersect itself, and you use LERF to separate those, to get rid of those self-intersections. So you can get rid of the self-intersections group theoretically, basically. And that's, so it means that finally generated subgroups are separable. You want to concentrate. Inseparable means what I was just saying, that any element that's not in the group, there's a homomorphism to a finite group where the image of that subgroup is separated from that element that's not in the group. And so residual finiteness says that the trivial group is separable. So it's an extension of residual finiteness. But ERF, extended residual finiteness, is too big a thing to expect because any three-manifold group, it turns out, has a simple infinite quotient. And so you couldn't hope to separate that kernel of that, but that's going to be infinitely generated. So LERF says local means finitely generated. And that's just the terminology that group theorists use. And it turned out to be the right concept
From a finitely generated subgroup
in the quotient, in a finite quotient. Yeah, that's
okay, that's Lerf.
yeah,
All right.
right.
I can sleep tonight.
But I like this geometric formulation a little better of Scott. It says that you can, any compact set, you can lift it to an embedding in a finite sheeted cover. That turns out to be equivalent.
Okay. That's exactly that drawing, yeah. Okay.
Yeah. Where you allow any arbitrary compact sets here, then you can find finite covers where they embed. That's equivalent. So that's why I gave that formulation versus.
Okay. And that compact set is in a cover with finally.
Yeah, in a cover with finally generated fundamental grid. That's right. But for the purposes of this lecture, we're interested in the surface case, which is why I drew the picture of the surface. All right, I still haven't gone over time.
Right.
Okay.